So I think everyone watching this video has raised a number to a natural power many times, and we've always seen this operation as just multiplying the base by itself an x number of times, x of course being the exponent. As students, we really don't pay much attention to this operation, we just see it as another annoying thing we have to calculate. But rarely do we stop to think, is there a faster way to compute this operation? And that's only natural. In most practical settings, when we raise a number to any power, it's normally to a very low exponent, so we don't feel the need to compute this result faster. But in the world of computer science, we start raising numbers to immense exponents, and we start needing a faster algorithm to compute these numbers. And that's where a simple yet genius algorithm comes into play. Of course, I'm talking about binary exponentiation. Now, before we look at the algorithm, some key properties we have to know are the following. Whenever we multiply numbers with the same base raised to a power x and y, what's going to happen is that their powers are going to add together. So in the case of 3 to the power of 4 times 3 to the power of 5, the result will just be 3 to the power of 9. A very intuitive way of seeing this is by looking at the number as the product of itself x times. This way, we can see that on the left side, 3 is multiplying itself 4 times, and on the right side, 3 is multiplying itself 5 times. When we multiply these two products, it's like simply adding a multiplication symbol between the two products, making 3 in this case now multiply itself 9 times. And the second property we must know is that any number raised to the power of 0 is 1, and in this case, we will also be including 0 into this property. Now that we know these two properties, we can now understand the algorithm we are about to see. Now, let's get a simple number like 2 as the base, and we want to raise it to the power of 10. Now, using the first property we saw, we can say that this number is equal to 2 to the power of 5 times 2 to the power of 5. But notice that we also don't know what 2 to the power of 5 is, so we also need to calculate this number. In this moment, if you've ever used recursion, then you should be able to immediately recognize that we're talking about a recursive algorithm. We will use smaller results to calculate the final one. Going back to the problem, we reduced the problem of finding 2 to the power of 10 to finding 2 to the power of 5. And we can keep going even further with this idea. Now that this is our problem, we can try and cut it in half again. But wait, 5 isn't an even number, and while the first property does hold for real powers, computing this is harder than just computing a number with a natural power. So instead of using 2 to the power of 5, we'll instead look at it like this. We will subtract 1 from the exponent, and we'll multiply the base to the result we get when we know what 2 to the power of 4 is, as multiplying by the base is essentially multiplying by the base to the power of 1. Proceeding further, now we can split this number to 2 to the power of 2 times 2 to the power of 2. And since it's even, we can split it in half once again. Now we need to compute 2 to the power of 1, and since 1 is odd, we can again just do 2 times 2 to the power of 0. Now we've reached the base case of the algorithm, and with the second property, we know this result for any number, so we'll return 1 when the power is equal to 0. Now it's time to go up. Since now I know what 2 to the power of 0 is, now I can multiply this result with the 2 I left hanging before. And now we know what the result for 2 to the power of 1 is, which is 2. Now that we know this, we can also compute 2 to the power of 2. Since we have the result for 2 to the power of 1, we just multiply this result by itself, giving us the answer 4. And again, since we know this, we can multiply the result by itself again to get 2 to the power of 4, which is 16. Here we have another hanging 2, so we'll just multiply it, and now we know 2 to the power of 5. And now, for the final step, since we know 2 to the power of 5, we will again multiply it by itself to get the result 2 to the power of 10, which is 1024. If you paid attention, you would see that for every step we went down, except for when the exponent was odd, we were splitting the exponent by half until we got to 0. Therefore, we can say that the number of steps to compute a power is logarithmic, or as you say in computer science, it would be big O of logarithm of n. This, as we know, is a way better runtime than the original algorithm we had that ran in big O of n. Now, let's see how the code for this algorithm works. First, we take care of the base case, which is when the exponent is 0. We will return 1 when this happens. Then we will take care of the case when the exponent is odd. In this case, what we'll return is the base multiplied by the recursive call, with the exponent being decreased by 1. Finally, when the exponent is even, we will assign a variable y to be equal to the function when the exponent is cut in half. And then, we will return this variable y multiplied by itself, giving us the correct answer. It's incredible how such a powerful algorithm can be written with only 4 lines of incredibly elegant code. This here is the beauty of computer science.